So in this screencast, I want to talk about Bayes' theorem, but actually I want to use I don't want to use Bayes' theorem in my solutions, because I think if you have a look at Bayes' theorem in our textbook, page 329, and you'll probably see why I don't want to use it, because it's it comes up in your formula booklet. But for my way of thinking, if we can do things without relying on formulas, and I think in probability we can do that, then life is a bit simpler. So I've called this screencast Bayes' theorem or not, because I'm actually not going to use the formula, but we're going to look at some of the conditional probability questions for which Bayes' theorem is used, and why it is in your formula booklet and in the course. Anyway, let's have a look at some questions. I'm going to go to exercise 6M, and I'm going to go with a couple of questions that are not on our WET requirements, and they are question 2 and question 6. So let's go through them. I'd expect you to be open at page 331 now, so that you could be referring to the questions that I'm talking about. And in the first one, we've got two machines in a factory that are producing bolts. So those bolts are stored in a warehouse. The first machine produces 60% of all the bolts. So machine one produces 60% of the bolts, and it has 5% of them are defective. 5% are defective. And machine 2, it produces obviously 40% of the bolts, and only 2% are defective. So it produces fewer defectives. Okay, the first question, part A, what is the probability that the bolt will be defective if we randomly select a bolt from this warehouse? If the probability that it's defective out of machine 1 will be, well, there's 60% of the bolts are from machine 1, so there's a 60% chance we're going to select a bolt from machine 1, and there's a 5% chance that it will be defective. So that's 0.03 as our probability coming out of machine 1. Now out of machine 2, 40% chance that it's going to come out of machine 2, and 0.02 that's defective, which gives us a 0.008 probability that we will pull out at random a defective bolt from machine 2. Now we take these two probabilities and add them together, because clearly a defective bolt could come from either machine. We add them together, we get 0.038. Okay, that's our probability of a defective bolt. Now part B is where our Bayes' theorem, our conditional probability, kicks in. It says, what is the probability that the bolt was produced on the first machine given that it was defective? So the probability that it was produced on machine 1 given that it's defective. Okay, so here I'm thinking, right, well, here's the probability that I'm going to get a defective bolt, and so now that is now my sample space. So 0.038 is now my sample space. And how is that made up? Well, it's made up of 0.008 parts machine 2 and 0.03 parts machine 1. So these two sum to my sample space. What part of that is machine 1? It's this part here, 0.03. So if I look at this, 0.030 and 0.008, they give me my 0.038 total. That's my sample space. What part of it is machine 1? Machine A? What have I called it? Machine 1. Machine 1, machine 2. Well, that accounts for 30 parts of my 38. So there's my probability. So this will be equal to 30 over 38, or 15 over 19. So no Bayes' theorem used there, just adapting my sample space as any given that question or conditional probability does. It changes the sample space. It's now, my sample space is 38 parts in 1,000. 30 parts in 1,000 are from part 1, contributed from machine 1, 8 parts in 1,000 are contributed from machine 2. So if it's defective, the probability it came out of machine 1 is 30 and 38, reducing to 15 over 19. Okay, let's have a look at question 6, and you might like to have a go at question 6 before you hear me through on this solution. So I encourage you to pause the YouTube now, have a go at question 6, and then come back to my solution and see how we go. Okay, so hopefully you've had a go at the question. It's we've got 2 dice. So die 1 is a biased dice, and the probability of getting a 6 on the biased dice is 2/3, and on die 2, which is an unbiased dice, and the probability of getting a 6 is, it just says it's unbiased, so it's 1/6. Okay, part 1, a dice is taken from the bag at random and rolled. So in part A, we're just saying the probability, let's say you have a look at, I don't need to write that. So the probability of a 6 coming from die 1, well, firstly we've got to choose die 1, so that's, so probability of a 6, the way I like to write this out is probability of a choosing die 1 first, followed by a 6. And over here we're going to look at the probability of choosing die 2 first, followed by a 6. So what we get is, well, it's a half probability that we'll choose die 1. You could put this in a tree diagram. You could go die 1, die 2, and then you could go 6 or not a 6, 6 or not a 6. So the same thing, and you'd be putting probabilities up here of a half, and die 1, probability of a 6 is 2/3, not a 6 is 1/3. Die 2, probability of a 6 is 1/6, not a 6 is 5/6. So you get the same thing. Die 1 followed by a 6 would be a half times 2/3, which is 1/3. Probability of a die 2 followed by a 6 is a half by a 6th, which is 1/12. So the probability that we're going to roll a 6 is the sum of these two probabilities. So that's 1/3, that's 1/12. If you sum those together, you get 4 and 1 is 5/12. 5/12 is our probability. So we sum that and we get 5/12, which is the probability of obtaining a 6. Okay, the second part is the Bayes theorem part. What is the probability that the unbiased dice was taken, that it was from here, given that you did not obtain a 6? Well, let's go back and look now at probability of not a 6 from die 1. Again, probability of not a 6. So we're now going down. We're now going down this path here. So it's a half by a third. So probability of die 1, not a 6, will be equal to 1/2 times 1/3, which equals 1/6. And the probability that we go die 2 followed by not a 6 will be equal to 1/2 by 5/6, which is 5/12. Now we need to put these in the same denominator so that we can compare them. Now we've got 2/12 here and 5/12 here. So now we've got a sample space. So we add these two together and we get 7/12. So the probability of not gaining a 6 is 7/12. As we could see, the probability of gaining a 6 was 5/12, not a 6. So therefore 7/12 equals the probability of not obtaining a 6. Okay, 7/12. So now our sample space is that 7. Those 7 parts are our sample space, made up of 2 parts from die 1 and 5 parts from die 2. So what is the probability, given that it wasn't a 6, we didn't obtain a 6, what's the probability that it was taken from the unbiased dice? Well, this is the unbiased dice here, so the probability is 5 parts of those 7. So therefore, the probability that it was not a 6, given it's probability that it was from the unbiased die, given that it was not a 6, will be equal to 5 parts in 7. Just to repeat, this is our sample space now, 5 parts of which come from the unbiased dice, 2 from the biased dice. So 5/7 is the probability that it came from the unbiased dice. Okay, so that's Bayes' theorem without using the formula. Hopefully you found that helpful. Now we can get on with the questions 1, 4, 5, I think. 1, 4, 5, and 10, and 11, and 15. 1, 4, 5, 1, 4, 5, 10, 11, 15 from exercise 6M. Okay, see you soon.